This is the video for the review for our probability units, the last 3 lessons we just learned, and I think they are Venn diagrams, tree diagrams, area models, lesson we called All-American Breakfast, probability in games, and driving risk. So let's look at the first question or series of questions. Pan is playing a new video game where the object is to make magic potions. Pan can make a potion correctly 20% of the time. Let's do that right. Okay. What is the probability that Pan will make 3 potions in 3 tries? So the way we do that is we're going to look at each event individually. So if one event and they can make the potion correctly 20% of the time, that's 0.2 or 2 out of 10 tries. So it's 0.2, and we'll multiply through each event. The second event is another potion that's 20% of the time. So that's also 0.2. And let's go ahead and start with this probability of potion. In other words, she gets a potion. And that's 0.2 times 0.2. And then the third time would also be 0.2. So if we do this on our calculator, I'm going to do it on my phone real quick. 0.2 times 0.2 is 0.04. And 0.04 times 0.2 is 0.008. I believe, let's double check that real quick. 0.02 or 0.2 times 0.2 times 0.2 is 0.008. 0.008 or 0.8%. Okay? That's a very slim likelihood that Pan will be able to make 3 potions in a row. So if 50 players play this game, how many players can the designers expect to make a magic potion on the first try? Well, if 20% of the players, it's a 20% probability to make a potion correctly, okay? If 50 players play, then 20% of those 50 players will actually get it. So let's highlight this real quick. Let's go ahead and we'll do this real quick so it looks right. I'm going to highlight it in green so you know that's the answer to question 1, okay? Oh, there it is, right there. Got it. If 50 players play this, how many people, how many players can the designers expect to make a magic potion on the first try? So probability of, no, let's not do that. How many out of 50? So it's 20% of 50, or 50 times 0.2, which equals 50 times 0.2 should be 10. Double check that. 50 times 0.2 equals 10. There you go. So that's an easy way to do these. It shouldn't be too hard to figure that out. All right, let's look at this fall corn maze. This is a rudder fall corn maze. If you only move forward, and only forward motion is allowed, no backtracking, drawing a tree diagram and area model for the maze might help solve the following 2 questions. What is the theoretical probability of landing on A to get a prize? Okay, well, so let's look at how many different pathways there are. Okay, so by looking at this, we need to look carefully. The first event, we have 3 pathways, right? So going to the top, all right, is 1 out of 3, right? The middle is also 1 out of 3. And the bottom is also 1 out of 3. Okay? So now we've got that down. I don't want to do that. Let's. Now look at that. Okay. So the top to go to is only going to go to B. So that we know that's not part of the answer. So I'm going to highlight that in red. So we know that's not part of the answer, because the top goes to B, which is not an answer, right? We're looking at how to get to A, okay? A is green. We'll go ahead and highlight that as green, okay? The middle, we'll look at, it looks like it has a couple pathways that one goes to B and one goes to A. So that's 1/3. And we also have times half of them go to A, right? Half go to B. That's 1/3 times 1/2. That's 1/6. Okay, that's going to B. Let's put this as B also. And I'm going to go ahead and do this again. There's another middle, which is 1/3 times 1/2, which equals 1/6. And that's for A. And that's a winner. So we'll highlight this as red because it's not good. Well, it's good. It's just not a winner. And we'll highlight this one with green because it is a winner. Okay? All right. Now, the bottom pathway, there are actually two pathways that come off this bottom pathway, 1 and 2. So going to A, there's one of them that go, and the other one is one of them. So bottom has two pathways, 1/3 times 1/2, which equals 1/6. And that's going to A. And there's another bottom, is 1/3 times 1/2, which also equals 1/6. And that's going to B. All right. So we know A is a winner. Okay, we'll highlight it in green. And B is a loser. So notice that all the B's, bottom. Let me make sure I spell that right, y'all. All of the B's are losers. They're all red. Okay. Only the green are winners. So we have 1/6 that go to A in the middle row and 1/6. Those are the probabilities. So how do we do this? Remember, in order to do this, to calculate the probability of this, we must determine each pathway's probability, okay? And by that we mean calculate. Okay? What we've done here is we've calculated each path. And if you look, we should have 5 pathways. 1, 2, 3, 4, 5. And we do 1, 2, 3, 4, 5. So only the green pathways are correct. Okay? Then let me make sure I capitalize. Then we add all the probabilities that are the correct ones, the correct answer. Okay? So in this case, we have 1/6 and 1/6. So we're going to add these two together. 1/6. Let me take off that highlight real quick. 1/6 plus 1/6 equals 2/6, which we know is actually 1/3. Okay? So 1/3 of the time is the probability. Okay? So the probability of A is that. Okay? So this is our probability of A is the sum of those two numbers. All right? So probability, we say we're going to take this, we're going to snatch it up, Command X, take it over here and put it down here, and put it as our answer. I will get rid of that first. That's our answer. Let me give us some little room here. Okay, if 200 people go through the maze on a particular day, how many prizes should the owners expect to give away that weekend? Well, we know that the probability of going to A, okay, and if that's the way we're going to get it, you must actually understand that 1/3 of the people that go are going to get a prize. So probability of prize equals number of people times the probability of A. That makes sense? Should. So it's 200 times 1/3, which equals, and I'm gonna bring this down so you can see it a little better. And I'll even highlight it in green so you know it's the correct answer. All we got to do is plug it into the calculator. Okay, so 200 times 1 divided by 3 equals 66. Uh-oh. Let me redo this. I'm going to have to fix that. Oops, there it comes back. Should be in just a minute. All right. 66.67. That's how many people we should give a prize to. Now, hold on a second. How do you give 0.67 prizes away? Well, here's how you fix that. What you want to do, you want to make sure that you actually give away a whole number. So let's make that 67. We're going to round up to 67, okay? Say 467 pumpkins given away. Make sense? All right, let's look at the next question. Students at South Vermillion High School, this is my alma mater. We're talking about students that use different internet programs to make their prints for their photos. We have a Venn diagram explaining this. What is the probability the student is an Instagram user? Okay, is an Instagram user. Okay, probability of an Instagram user is anything inside the circle. So all we have to do is find out how many people are in this Instagram circle, and we put it over the total number of people there. So let's look and see what the total number of people that are in Instagram. That's 88 plus 11 plus 38 plus 7. So that's 144. Okay? So 144. I'm going to highlight it in green. 144 divided by the number of total. So we add the 12, the 53, the 92, and the 47. So it's 1,048. Oh, I did something wrong here. Let's start that over. 88 plus 11 plus 7 plus 38 is 144 plus 7. Oh, I already got the 7 in there. I can't add 7 twice. Plus the 12 plus the 53 plus the 92 plus the 47. 348. So our probability is 144 over 348, which could be reduced because they're both divisible by 2. We divide 348 by 2, that's 174. We divide that by 2, it's 87. 144 divided by 2, and 144 divided by 2 is 72. Divide that by 2, and it's 36. So it's 36 over 72, I think. No. 36 over 87. 36 over 87. Okay? Now, I'm pretty sure that 87 is divisible by 3. Oh, let me clear that out. 87 divided by 3 is 29. And 36 is divided by 3, so we can actually go down a little further. 36 divided by 3 is 12, so it's 12 over 29. That's reducing fractions. It's something you should have learned a long time ago. What's the probability the student is both Instagram and Shutterfly? So if they use both Instagram and Shutterfly, the only thing that we should concern ourselves is, number one, what is the sample space? We've already considered that. That's 348. And then how many people use both Instagram and Shutterfly? Now, it doesn't say only Instagram and Shutterfly. It says both Instagram and Shutterfly. So that is the 38 and the 7, the intersection of these two circles, the Instagram circle and the Shutterfly circle. So it's 38 plus 7, which is 45. So the answer is 45 over 348. And I'll let you do the reduction of the fractions. What's the probability of a student use no photography websites? There's only one place they do that, and that's the 47. That's outside, because all the ones inside the circles use some form of website. So it's 47 over 348. What's the probability the student does not use either Instagram or Snapfish? Let me rephrase that. Let's say that a student uses, proper English, neither Instagram nor Snapfish. Okay, now that I got that right, let's look at it, highlight it in green. So neither Instagram nor Snapfish. In other words, they use only Shutterfly, right? So they don't use Instagram or Snapfish, but they use either Shutterfly or none at all. So it's 92 plus 47. So 92 plus 47 over the sample spaces, which is 139 over 348. What is the probability that the student used Shutterfly, Snapfish, or Instagram, but not more than one? Okay. So in other words, they used only one of the services and not any of the others. So we have to add only the ones that are inside the circles, but not inside any of the intersections, and definitely not the one that's outside. So it's 92 plus 88 plus 53 over 348. So that is 92 plus 88 plus 53, or 233 over 348. Okay, so 233 over 348. Here, question 10, we're looking at this Venn diagram. Venn diagram says, of 100 people surveyed at the Frodo Baggins Community College, the following information was collected: males and females, vehicles and no vehicles, accidents and no accidents. So if you look carefully at this Venn diagram, each circle encompasses just that part of that's described, the vehicle. So the numbers in here are just people with vehicles. Now, whether they're male or female depends on which other circle they're inside. So this circle just encompasses male. So these numbers here are the total males surveyed. So the intersection of vehicle and male is the number of males that have vehicles, which would be 18, the sum of those two numbers. The intersection of all three of them, this circle right here, is just people that have had accidents. Okay, so you can't have an accident without a vehicle, which is why you know that males with vehicles are the only ones that get accidents in this particular part of the intersection. Okay, that's what 3 stands for: males, vehicles, and accidents. Now, anything outside of the male circle, for ease of this lesson, is female. So this number 11 is females with vehicles that did not get in accidents because they don't intersect that accident circle. And this one right here is a female that got in an accident because she had a car. This number outside here, now that one's pretty easy to figure out. If it's not male and it's not a vehicle, then it's a female with no vehicle. Obviously, there's no number inside this part of the circle of accident because you have to have a person and you have to have a vehicle to get in an accident. Likewise here, in a male intersection of male and accident, there's no vehicle, so you can't have an accident. So let's look at this. Males are more likely to get into an accident than females. Now, you may look and say, let's look at the sample size of the entire thing. But you might be considering something that is probably not everything you need to know. So think of it this way. You have 49 plus 21 plus 15 plus 3, or I apologize, 15 plus 3 plus 11 plus 1, total people, male and female. All right. So if we look at the number of accidents over the total number of people, you're going to easily see that males outnumber females as far as likelihood to get into an accident. But we need to look at just specifically males, and then we'll look at just specifically females as our sample size, because we're looking at likelihood to get in an accident, whether they're females or males. Now, this is a true or false question, but the likelihood needs to be understood completely before we get involved in it. So let's look carefully. How many males do we have? We have 11 plus 15, that's 26, plus 3 is 29, plus 1 is 30. So sample size for males is what? 11 plus 15, 26, plus 3 and 1 is 4, is 30. Okay? And then the sample size for females There's more than that. We've got 49 plus 11, which is 50 or 60 plus 1. So there's 61 females. That's a lot more females than there are males in this particular survey or poll or whatever it is. So if that's the case, then we need to look at how many were in an accident and then how many, we're not worried about anything else, just what the accident is. So the probability of a male accident is the number of males, okay, they got an accident over the sample size of males. All right, and we'll look at another way to look at this in just a second. But I want you to look at how we determine this one, and then we'll look at it in a different perspective. So there's only one female, and there's a total of 61 females in an accident. Oh, not 16, 61. So it looks like there's more males per accident. But we need to look at the females and the males that actually have cars, not just males or females. That's an objective look, and it does skew that. So this is not the correct answer. I'm going to highlight this in red. We did the math, but I want you to see why it's not correct. It's not correct because how can a male or a female get into an accident if they don't have a car? So let me change this. I'm going to put the correct color, green. This is the probability of a male driver accident. Now that looks exactly at what we're looking at. So males that drive, okay, are just these numbers right here, 15 and 3, which is 18. And only 3 of them got in an accident. So 3 out of 18, okay? Okay. Actually, this number right here would be 3 out of 30. All right, I apologize. I forgot that number right there. It is a 3 for males. And the probability of a female driver gets into an accident is 1, and that's out of 12. All right, do you see that now? 1 out of 12. And we can reduce both of these. 3/18 is 1/6. And 1/12 is 1/12. So, which is bigger, 1/6 or 1/12? 1/12 is actually what? It's 1/2 of 1/6. So, yes, males are actually more likely to get into accidents than females, okay? So, 3 out of 18 and 1 out of 12. 3 out of 18. Females get into accidents more often than males. Well, 1 out of every 6 drivers and 1 out of every 12 drivers, no. Males are actually more likely to get into accidents than females. So the answer is true. All right, so male drivers have a 1/5 probability of getting into an accident. We just calculated it as 1/6, right? Now I'm gonna unhighlight this part right here so you can see it all, except for the answer, and unhighlight this so you can see the female answer. Okay, and I'll even do it so you can see that. Male drivers have a 1/5 probability of getting into an accident. No, that's not true. Just look up above. Actually, you know what? I think this was written incorrectly. This should be 1/6. I don't know why it's written as 1/6 or 1/5. This is actually true. Okay, so let's highlight that as the correct answer. I need to go back and fix that too. Female drivers have a 9.1% probability of getting into an accident. True or false? Well, let's see. What is 1 divided by 12? Okay, 1 divided by 12, if that's 0.09, then it's correct. Let me do my calculations here on my trusty phone. 1 divided by 12 is 0.0833. That's actually not correct. So we'll highlight that as the correct answer of being false. Which statement is more convincing that females are less risky as drivers? Now, just because the answers may not be absolutely correct according to number 10, it's still, we're looking at a way to persuade people. So we can give factual information, even though it skews to what we're actually determining. Of the 100 surveyed, only one female got into an accident, but 3 males got into an accident. That's pretty convincing, okay? Of the 18 male drivers, 3 got into an accident. And of the 12 female drivers, only 1 was in an accident, okay? And of the 30 drivers, only 4 were in an accident. And of the 100 surveyed, 70 did not drive. C and D obviously are not correct answers. But if you look at A and B, both are true, but one of them gives us a very convincing detail, okay? The fact that only 1 female got in an accident, but 3 males got in an accident, that's 3 times the number. And both of them say the same thing. The denominator is different. In A, 100 is the denominator, and it says that very few people get in accidents, but that doesn't take into account that a lot of them don't drive. B is probably the most convincing because if you look at it from the perspective of how many people got into an accident over the number of people that actually drove, that's the best convincing argument. So let's go on to the next question. This is a pretty convoluted thing, but you have to be able to see it really well. I'm going to blow it up a little bit so maybe you can see it better. All right, so the question number 14, how many combinations of eggs, meat, and bread are possible? You must have one of each to complete your breakfast. Well, it's pretty easy in a tree diagram. You just have to count the number of ends there are. Or you can just count the number of levels and how many events are in each level. Well, there's 3 in each level, so it's 3 times 3 times 3, okay? Fundamental counting principle is if you have 3 events, you multiply the number of events in each, the number of options in each event through the whole tree, and you find out exactly what it is. So it's 3 times, well, let me get this in there so you can see it. 3 times 3 times 3, which is 27 total options, all right, or possibilities. Which is called the sample set. Total number of possibilities is called the samples, defined as a sample set. All right. Highlight that so you know it's correct. What is the probability that a customer will order fried eggs, ham, and wheat toast? So what is the percentage of fried eggs? That's 0.42. We're going to put that in as part of our 0.42 times ham. The percentage of ham is 0.15, and we're going to multiply the probability of getting wheat toast. Wheat toast is 0.23. So we just have to multiply through that to find our answer. So it is 0.42 times 0.15 times 0.23. That gives us a probability of 0.01449, which equals, I would say, as a percentage, 1.4%. Okay? Makes sense? Okay? And if you want to look at it from this perspective, you can look at it in another way. If you want to count the number of Italian toasts, those endings where what it is, over 27, that's not going to give you the correct answer. Even though tree diagram lesson teaches you that, this particular one gives a predetermined probability for each different option. And so we have to multiply through those probabilities. Finding the number that goes to the end over the total number of options does not work this way. So our answer here is the only correct answer. What is the probability that someone will not order poached eggs with sausage and white toast? Okay, so what is the probability of poached eggs? Poached egg is 0.22. So the probability of not poached eggs equals 1 minus, this is called the complement probability of poached eggs. So that's 1 minus 0.22. So that equals 0.78. So there's a 78% chance they'll order something else. Alternatively, you could find out what the probability is by adding the other two together. 36 plus 42 is 78. So that helps you any at all. So the probability of those particular options is 0.78 times sausage, which is 0.1 times white toast, which is the most popular, or the least popular, 0.17. Let's see what we get. 0.78 times 0.1 times 0.17 is 0.01326, which is 1.3%. Okay? Highlight that so you can see it well. Okay, so what is the probability of someone order either poached or scrambled eggs with either sausage or ham and wheat toast? So we add those probabilities together. So poached and scrambled together is going to be 0.22 and 0.36. So it's 0, let's put that in parentheses, 0.22 plus 0.36. And that's multiplied through sausage or ham, which is 0.1 and 0.15. 0.1 plus 0.15. We add those probabilities together in the same event, and then we're going to multiply by the probability of getting wheat toast, which is 0.23. All right, and we'll put that into the trusty calculator. Remembering that we don't have parentheses on this. Some of them, yeah, we do. So we have 0.22 plus 0.36, and we'll end that with a parentheses, and we'll multiply that times another parentheses. This is the way you have to do it. 0.1 plus 0.15, close parentheses, and then we'll add that, or I'm not add, I apologize. Multiply that product by 0.23, which is probability of, I believe, wheat toast. We come out with a answer of 0.03335, which comes out to 3.3%. So, pretty solid answer for that. Easy way to do it is just look at your probabilities, add those that are together, and we should sit there. Now, look at this last question. This last question is pretty carefully worded. If omelets are added to the first branch of this diagram, so there's a fourth event called omelets, okay? And it has a probability of 0.3, and the remaining choices keep their probability within the remaining 0.7. What are their new probabilities? All you're doing is calculating what their percentage of the 70% that remains is. So all you do is for probability of, oh, look at this. Oh, my font has changed. I'm going to fix that. So the probability of, let me get this away from there. Probability of, let's see, we have scrambled, fried, and poached eggs that are left, right? Yeah, fried, scrambled, and poached. So probability of fried eggs equals whatever its probability is times 0.7. So 0.42 times 0.7. Because we only have 70% left. So this is really simple. This becomes very easy. 42 times 0.7. Now the probability is 0.294. Probability of scrambled eggs is 0.36 times 0.7, which equals, I'm going to move these down. You can see it better. Zero 0.36 times 0.7. 0.252. The last one, poached eggs, which are like by far the most popular eggs. You sense my sarcasm there. We'll go back up here and look. Probability of poached eggs is only 0.22. with a lack of other options, probably your best bet is to get something you like. 0.22 times 0.7, 0.154. And if you want to look at it from the perspective of what that is in percentage-wise, I'll put that up there too. That's not greater than, it's just that goes to that. I guess I should kind of explain that a little better. And these are your answers for their new probabilities. Okay, so let's look at this next one, create a pasta dish. Now this one is just like the tree diagram. You can easily make a tree diagram to help you figure this out, but you have different types of items. There's the size, the pasta type, and the sauce type. And you can assume you can make all the possible pasta combinations using one choice from each column size, size, meat, and cheese. Someone puts all these subs in an unmarked box, or not subs, but pasta dishes, an unmarked box on the counter. Each item is in the category is equally likely to be selected. So now we know it's equal likelihood. So there's a 1 in 2 chance for size, right? In pasta, there's a 1 in 4 chance for, and then in sauce, there's a 1 in 3 chance. Because you have a sample size of 2 for size, a sample size of 4 for pasta, and a sample size of 3 for sauce. So what is the total sample size? How many total possible combinations are there? If only one item per category is allowed, that's the sample size. A sample size is going to be, we're going to multiply through that. That's pretty simple. 2 times 4 times 3. So in other words, you're just multiplying through the number of possibilities in each event. So 2 times 4 times 3 is 24. So that's our answer to this question. What's the probability the next customer will select the large spaghetti and not bolognese sauce? Okay, so it's a probability large spaghetti, not bolognese. So probability of a large spaghetti is 1/2 times just spaghetti is 1/4 times not bolognese. Well, their bolognese is one of the 3 choices, so that means 2 of 3 choices. And that is 2 over 24, which we know can be reduced to 1/12. That's our answer for this one. Highlight it green so you know that it's the right answer. What is the probability that the next customer will select a small with neither ravioli nor Alfredo, which means not Rav, or not Rav nor Alfredo. Notice it doesn't say about what kind of sauce. So in those kind of cases, when they say nothing about the sauce, we need to just immediately assume they mean any sauce. It doesn't say that, but any sauce is always assumed when you're not given a choice. So what's the probability of a small? That's 1/2. And we're going to multiply 1/2 times not ravioli or not Alfredo, which is 2. There's 2 options that you don't need, so that leaves 2 remaining out of the 4. Okay? And we're going to multiply that by 3 out of 3. Because you're going to use all 3. So 2 times 3 is 6, and we know that the bottoms multiply through to equal 24. And so the answer is 6 out of 24, or 1/4. So that's our answer. There's a 1/4 chance, 25% chance that anybody walks up to get that type of options will get that type of option. And what is the probability that the next customer will select a dish? A dish with spaghetti or vermicelli and Alfredo sauce. Well, they didn't say anything about the type of bread, so that means we're going to get just totally 2 out of 2 because the size doesn't matter. We're going to get 2 out of 2 for the size. Either option is available. That actually comes to 1. The point of putting that in there is to make sure that we don't make a mistake. Spaghetti or vermicelli, there's 2 out of the 4 options. And then we're going to multiply by 3 out of 3 because we didn't say anything about the type of. Oh, we did say Alfredo, not 3 out of 3, 1 out of 3. 1, because there's only 1 option out of the 3 possible sauces we're going to get. And so that becomes 2 times 2 times 1, which is 4, out of 2 times 4 times 3, which is 24. So 4 out of 24 is 1/6, and that's your answer for that problem. Remember that if it doesn't give you any kind of specific option for one of the events or one of the options columns, like size, pasta, or sauce, if they don't give you an option, it means any. That means any of those are available. So in other words, however many there are, if there's 14 and they don't say what kind of sauce of the 14 sauces, it would be 14 out of 14 possibilities. So let's move on. Let's look at this area model. This area model is pretty cut and dry. Tells you a whole lot about itself just by looking the way it does. The first thing you want to do is find the sample size in this particular area. The area is cut up into different colors. But look at the smallest area there is, this little size yellow, the white, the pink. Those are all different areas. Well, if you look at the other ones that are larger, you can see how many of those fit into it. This one has 2, okay? And I'm going to put a 2 there. This one has 2. Anything that doesn't have 1, I'm going to put a number by it. The white has 4. As you can see, there's 2 of those 2 pinks. This one has 2. The yellow here has 3. The white has 2. And then all the rest are just 1. So 2, 4, 5, 6, 7, 8, 9, 10, 14, 15, 16, 18, 19, 20, 21, 22. So let's double count that again. 4 times 6 should be 24. I don't know where I can get my count off from, but let's look at it again. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. So we know that the sample size for this is, I want to spell that with the correct words, 24. So whatever the probability is, we just need to define the sample size as the denominator. So probability of tossing a coin into white is however many white there are, white over total. Okay? So we know the total is 24. We just need to count the white. 2, 3, 7, 8, 9, 10, 11. So 11 out of 24. There's your probability. Okay? Really simple stuff here, folks. Not making this as rocket science. What is the probability of not tossing onto a pink area? So not pink. So we know it's not pink over total. We don't have to write that down. So what is not pink? We'll count everything that's not pink. White is not pink. 1, 2, 3. Yellow is not pink. 4, 5. 6, 7, 8, 9. 10, 11, 12, 13, 14, 15, 16, 17. So it's 17 out of 24. All right. Alternatively, you know that there's 24. You could count the number of pink and then simply subtract that from 24. Well, let's count the pink. 1, 2, 3, 4, 5, 6, 7. 7 from 24 is 17. We get the same answer. Okay. What is the probability of tossing a coin into a white or pink area on the above area model? White or pink. We just have the probability of both and add them together, or alternatively count all the white and pink together and then divide that by 24. So what is the number of white and pink? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Oh, no, 16, 17, 18. It's 18 out of 24. You divide both by 6, you end up with 3/4. Okay? So 3/4 of them are white or pink. Another way to do this is to look and see how many are yellow. 1, 2, 3, 4, 5, 6. 6 from 24 is 18. We get the same answer. All right. What is the probability to toss a coin into a yellow area in the above area model? We just counted 6 as our yellow. So it's 6 out of 24, which reduces to 1/4. So that's your probability of getting yellow. I like that is correct. What is the probability of tossing a coin on heads onto either pink or white area? So pink or white we already have is 1/4 or 3/4, right? But what's the probability of tossing a coin onto heads? Probability of heads we know is 1/2, right? And we need to multiply that through the probability of what? Pink or white. Well, fortunately, we already did the probability of pink or white. The probability of heads is 1/2. You got heads or tails, the only options, the sample size is 2. And heads is one of the options. The other option is tails. So probability of getting heads is 1/2. We're going to multiply that by pink or white. Probability of pink or white is 3/4. So we're going to multiply that times 1/2. So it's 3/8. Okay, so the answer is 3/8. All right, that is our answer. And I'm going to highlight that. And so that is it for the review. This should help you a lot. I don't think the questions on the test are going to be much more difficult than this. Take your time on it. Be sure to go through. A copy of this completed review should be available for you on the description below inside this video. So in the meantime, y'all, be blessed and be a blessing. Have a ball.